In this video, we are going to be looking at hypothesis testing and its relationship with confidence intervals. Just for anyone who doesn't remember, I'm going to slap up our formula, all right, for a confidence interval. So this is going to be just the generic formula. So for a 100 times 1 minus alpha percent confidence interval, it's going to be calculated as x bar plus or minus, or plus and minus rather, z alpha divided by 2 times our standard error, which is sigma over the square root of n. Alright, so this is the version when we can use our standard normal distribution, and we can use our z distribution for our critical value. If we can't, right, if we have a small sample size and our population standard deviation is unknown, we would need to use t if we can assume that the variable is normally distributed and on its own. And in that case, our formula would be slightly different. It would be x bar. I'm just gonna write it down. I'm gonna erase it in just a second. All right, but x bar plus or minus t alpha divided by 2. Then we have our degrees of freedom times s, or the sample standard deviation, times the square root of n. All right, and as it has been for everything in this chapter, that might change if you go on to, or will change when you go on to stats 2, if anybody is doing that. But our degrees of freedom is n minus 1 for that. All right, but so what we're going to talk about, we're only going to talk about it in terms of the z distribution, but just keep in mind that we can do the exact same stuff when we're using the t distribution. All right, so with this formula, all right, it shows us that 100 times 1 minus alpha percent, I've already written percent, don't need to write it twice, 100 times 1 minus alpha percent of all confidence intervals will, let's backtrack. All right, so 100 times 1 minus alpha percent of all confidence intervals calculated using this formula contain the population mean, right? Which is what we are trying to do. We're hoping that our confidence intervals contain that population mean, right, when we are doing them, when we're calculating them. All right, so if we, for instance, were setting our alpha at 0.05, all right, so that would be a 5% significance level or a 95% confidence level. Right, that would mean that 95% of all confidence intervals calculated this formula when we've got 1.960 in there. That would be the critical value. All right, so 95% of confidence intervals using that formula are going to contain the population mean for whatever we're looking at. All right, so how does this relate to hypothesis testing? Right, well, when we are looking at a two-tailed test, right, so we're looking at a null hypothesis that says mu equals our arbitrary constant, and our alternative hypothesis says that mu does not equal that arbitrary constant. Right, so if, right, just like when we're doing a hypothesis test, we are essentially acting like the null is true, right? The null is true until we can prove otherwise. Our test statistic is a standardization of our sample mean under the assumption that our arbitrary constant is the population mean, right? So under the assumption that H naught or the null hypothesis is true, right, we're going to standardize that value, right? So we're seeing how likely is it, right? Well, if the null hypothesis is true, if mu does equal C, then we should expect to see C in our confidence intervals, right? So if H naught is true, our confidence intervals should include C, right? So if we're using the same data to calculate a confidence interval, right, then that C should be in there if the null hypothesis is true. All right, so we are going to look for instances when our arbitrary constant is not in the interval, right? If H naught is true, right, we would expect to see C, our arbitrary constant, in our confidence intervals. If, on the other hand, the alternative hypothesis is true, we would expect to not see, right? Or that's a weird way of saying it. We would not expect to see that arbitrary constant in our confidence intervals. All right, so if we reject the null hypothesis when our confidence interval does not contain C, right? One, just that first clause, that would make sense, right? We wouldn't expect C to be in our confidence intervals if H1 is true, right? So we're going to say, well, then let's reject the null hypothesis, right? And conclude that our alternative is true when C is not in our confidence interval, right? So if we do that, then we will reject HO when it is true with a probability of alpha. Right, and we know that, right, what does it mean when we reject a true null hypothesis, right? Well, that is a type 1 error, right? And we're saying that the probability of doing that, right, when we reject the null hypothesis if C is not in our confidence intervals, we're saying the probability of that is alpha. All right, this matches up with what we've already talked about previously in this chapter. Right, the probability of a type 1 error is equal to alpha. All right, so either way you do it, whether you do a traditional hypothesis test where we state our null and alternative hypotheses, then we kind of determine our significance level, then we find our our critical value, then we calculate our test statistic, and then we reach our conclusion, right? The probability of making a type 1 error is alpha for that. It's also alpha for this, right? So these are equivalent methods, right? One thing to note, you can only evaluate a hypothesis test with a confidence interval if it is a two-tailed test. All right, so we can only evaluate two-tailed hypothesis tests with a confidence interval. Right. That's not quite what that means, is it? This makes it sound like the only way to evaluate a two-tailed hypothesis is with a confidence interval. That's obviously not true. We've done that already with a regular hypothesis test. That's going to bother me. I'm going to rewrite that. That's not right at all. All right. Let's see. So a better way of saying that: confidence intervals can only be used to evaluate hypothesis tests if they are two-tailed. All right, so hopefully at least one of those ways of writing it made sense to you. All right, but again, the main point is that if you have a two-tailed test, then you can use an interval to evaluate it, right? So let's look at a couple of other things involved with this. One, I'm just going to I haven't actually written this down. So when we're using our confidence intervals, what's our conclusion criteria, right? So we kind of already stated one. We've probably worked this out, but just for thoroughness, I'm going to write this all out. All right, so if C does not appear in the confidence interval, then we will reject the null hypothesis and of course conclude that the alternative is true. Right? On the other hand, if C does appear in the confidence interval, then we will fail to reject the null hypothesis. Right? And this also makes sense, right? So if the population mean is going to appear in 95% of confidence intervals using that formula, right? Then the C being in there, we're not sure, right? It doesn't guarantee that the null hypothesis is true. It doesn't guarantee that mu equals our arbitrary constant. Really far from it, but it doesn't allow us to say that it's not equal to that. All right, so we have to fail to reject that null hypothesis. All right, so now let's move on to brief examples. All right, so let's say that we've got this hypothesis test we are going to evaluate. All right, so it is a two-tailed test, so that's good. It's a good sign. All right, so we got this two-tailed test. Null hypothesis is mu equals 100. The alternative is mu does not equal 100. All right, and we're going to have two confidence intervals. Right, and they're both just going to be 95%. We're going to assume that we are evaluating these at the 95% confidence level. Right, so the first one has a lower bound of 102.1 and an upper bound of 109.7, and our other one has a lower bound of 98.3 and an upper bound of 105.6. Right, so if we got this first result, right, if we got this first confidence interval 102.1 to 109.7, right, and we were going to try to evaluate our hypothesis test, right, we would see, right, well, 100 does not fall between 102.1 and 109.7, so we would reject the null hypothesis, right, and we would conclude that our mean does not equal 100. Right? Again, because that 100 does not fall into our confidence interval, right? So 100 does not fall into that confidence interval, so we reject our null hypothesis, right? If we go down to the next one, 98.3 to 105.6, right? 100 does fall into this confidence interval, right? 100 is in between 98.3 and 105.6, right? And so our conclusion would be fail to reject. Right, and so that's how we can, and so we didn't actually go through the process of calculating any of these confidence intervals because we covered that in chapter 9. So here we're really just focusing on that actual evaluation of hypothesis tests using these confidence intervals. One thing I do want to note before we wrap up here is that let's suppose you are, right, let's say that we've got, let's just say we've got the same one. So mu equals 100 for the null, mu does not equal 100 for the alternative, right? And we have a 90% confidence interval that was 110 to 131, a 95% confidence interval that is, we'll say 102 to 107. Doesn't really matter for what we're doing. Actually, that would not make sense. Let me restart that. We're going to restart that real quick. Right, so we're going to have 3. We're going to have 99%, 95%, 90%. Because this is going to make it easier on me, I'm going to start with this one. So we're going to go with right, so 102 to 117. Well, then we'll say the next one is 106 to 113, and then the 90% is 108 to 111. All right, so let's just say that those are our confidence intervals, right? And we want to evaluate at the 95% confidence level. Right, so that's what we want to do. So which one of these are going to be, can we use for our evaluation, right? So one, we can look at it when we just looking at all of these confidence intervals. 100 does not fall in between into any of those confidence intervals, right? However, we can only use the 95. Ooh, that is, why does it keep doing that? Right, we can only use the 95% and the 99% level to reject the null hypothesis at the 95% confidence level, right? So really the main point here is that if you go to a stricter confidence level or a stricter significance level, right? Then you can use a stricter one, right? A kind of more strict one to say, yeah, that's significant at this level too, right? So if we have 95, if we have a result from a 99% confidence interval, right? Well, we could say, well, if we reject the null at 99%, we're also going to do it at 95 and 90, right? But if you try to go the other way, it doesn't work. So just because you could, let's say you just had the 90% and you didn't have the other two, right? You could not say anything about this hypothesis test at a higher confidence level, right? You could reject the null at the 90%, but you could not at the 95 or 99%, just based off of the 90% alone. All right, so if you just had that one, then you could not say you would reject at any of the other levels, right? But if you have some of the other ones, right? So if you have 99, you could say, well, you would reject at all the other ones. Right, so again, that's kind of a rambly way of saying that you can go from more strict, right, from stricter results to making evaluations or making inferences about less strict confidence levels, but you cannot go the other way. Right, that is it for this video, and that's it for this chapter. Depending on, if I reuse these for Stats 1, then great job making it to the end of the semester. If you're in Stats 2, then we've just gotten started. So I will either see you for the final, or I will see you for Chapter 11.